Hello and welcome to this lecture series on chemical process modeling and simulations. For the past two lectures, we have been discussing the fundamentals of thermodynamics as part of modeling energy of systems. This lecture is poised to be a long one, but it attempts to unravel the enigma that is in thermodynamics called entropy. So, entropy is often less understood, probably misunderstood concept in thermodynamics. In this lecture, we will try and use a number of examples, some quite simple, some bit more complex, some very practical, some very hypothetical, but all of which will be directed towards giving a picture of what entropy is, why entropy is a fundamental property in describing the state of a thermodynamic state of a system, and in what forms, in what ways does it get utilized in thermodynamics and by extension in engineering. While there is a lot of attempt that has been made, I would say, in this lecture to illustrate ideas and help understanding of concepts, I have tried my absolute best to keep the math to as minimum as possible, and there are a couple of places where I outright do not show the math at all and just request you to take for granted certain things. But for a better, in terms of more thorough picture of entropy, where the math is revealed in more detail, I would recommend you to consult this excellent book, Molecular Driving Forces, Statistical Thermodynamics in Biology, Chemistry, Physics and Nanoscience by Ken Dill and Serena Bromberg, second edition, published in 2010. There are also other books that I periodically cite as we go along. They also will definitely contain some additional perspectives as well as some more rigorous, mathematically rigorous perspectives of entropy. With this introduction, let's delve right into what we understand by entropy. So, what are underdetermined distributions? Consider a macroscopic system comprised of molecules, a glass of water, classic underdetermined distribution. The number of microscopic states are so numerous that they are all impossible to measure. So, from a molecular perspective of a system, we seldom know the full state of the system or full distribution of the sequences. What are the sequences? Translational, rotational, vibrational, kinetic energies, and then positions. Aren't the relative positions give the potential energies for the molecular orientation, the bond length, bond angle distributions, bond length, all those, right? So, we never know the full distribution of the sequences. These distributions are severely underdetermined. Now, again, we are going to take up yet another example of simplified, oversimplified system. Again, something similar to a coin toss. We are now looking at a die that is being rolled. All right, to understand what does this underdetermined distribution of S is equal to minus K sigma pi ln pi, or S is equal to kb ln omega. What does this mean to an underdetermined distribution? To understand this, let us consider rolling of a six-sided die. Okay, marked, each side is marked 1, 2, 3, 4, 5, 6. So if side number 1 comes, the number on top that you see is 1. Side number 2 shows up, the number you see on top is 2, and so on and so forth. Rather than knowing the full distribution after n rolls, suppose you rolled it 100 times, rather than knowing all the 100 outcomes, okay, we either know the total score, the sum of all the numbers 100 times whatever happened, or we know the average score. Basically, you divide the total score by n, by 100, right? So you will get the average score. So this is a severely underdetermined system. So we don't know the entire details. Right? So in such an underdetermined distribution, if we were to apply this formula, this expression for entropy that Boltzmann proposed, which is S equal to kb ln omega, or the equivalent expression from probability information theory, which is S equal to minus kb sigma pi ln pi, right? What does this imply? Let us consider the case of, well, supposedly an unbiased distribution. I put a question mark here. Suppose after thousands of rolls, the average score is 3.5. 3.5 you will get 3.5 by adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. Okay. Why have I put a question mark? Just because the average score is 3.5 doesn't mean that the distribution has to be unbiased. There are other ways in which you can get this 3.5. This is evidence but not necessarily proof that the distribution is unbiased. See, here is an example. 2 plus 2 plus 2 plus 5 plus 5 plus 5 divided by 6 also gives rise to 3.5. That is clearly not an unbiased distribution at all. Right? Fine. Okay. So, but suppose we have an unbiased distribution. As per our ability to see, which we can only see, like the elephant, we can only see like the blind man seeing some part of the elephant, some aspect of the elephant, right? So we only know the average score, which is 3.5 after n rolls. N could be 100,000, 10,000, 100,000, so on and so forth. What does this mean? If it is a truly an unbiased distribution, all outcomes should be equally likely, right? Let us see if we can, if applying S is equal to this expression results in this. The second example, let us take a biased distribution. Suppose after thousands of rolls, the average score is 2, which clearly is evidence and proof that the distribution is biased. Right? This is proof that the lower scores, which is 1, 2, and 3, are more likely than the higher scores, which is 4, 5, and 6. Though we don't know how more likely they are, let us see, can we try and get at least some understanding, some information of how more likely are the lower scores compared to the higher scores? Is there some picture that we can get by employing this expression for entropy? So what does the hypothesis of maximum entropy or maximum multiplicity show in these two cases? Let's take the case of unbiased distribution. The probabilities should add up to 1. All the outcomes, if I sum up all the probabilities, the total probability should be 1. Therefore, sigma pi should be 1. Either I use this constraint, or if I can say that sigma dpi, change in pi, alright, is 0. This is a constraint I impose on the distribution. Always this is a constraint that is imposed on this distribution, which is basically the underdetermined distribution, which is how we are describing the state of the system. So I asked the question, what is the distribution P1 star, P2 star, P3 star up to Pn star? This is the outcome that I'm going to explain, I'm going to obtain, that maximizes this entropy while satisfying this constraint, sigma pi equal to 1 or sigma dpi equal to 0, here n being the number of times the die has been rolled. This is an equality constrained optimization problem. I am maximizing a function subject to an equality constraint. Not an inequality constraint, but an equality constraint. In such problems, we should find the maximum or minimum, in this case maximum, right, of the function here s subject to the given constraint. This maximum of S may not be the global maximum, but if you look at all the possible values of S that satisfy this constraint, it will be the maximum among those values, right? So this is what we have to try and find out. So now what we are going to do over the next 3-4 slides, we are going to take a slight detour from this into the mathematics behind equality constraint optimization problems. We are going to see one of the approaches that can be used to come up with this maximum and find out what is this distribution. That is what we are ultimately interested in. We're going to try and come up with this the mathematical approach that can help us answer this question, and that is the method of Lagrange multipliers. So any good calculus book talks about Lagrange multipliers, and of course you can also consult the Wikipedia page on Lagrange multiplier. So here is the problem statement, right? Find the maximum of the function x comma y subject to the equality constraint g of x equal to 0. We didn't have g of x equal to 0. We had sigma pi is equal to 1. Okay, so the constraint will be sigma pi minus 1 will be 0, isn't it? So the approach is this: define the Lagrangian function. We are going to define a new function which is given by f of x comma y. This can be g of x comma y, could be anything, right? Minus some constant lambda times g of x comma y, which the lambda is a constant which we call as Lagrange multiplier. And now we determine the stationary points of this new function L. What are stationary points? Stationary points of a differential function of a single variable. Okay, if you have only one variable instead of more than one variable, right? Single variable are those where the function's first derivative is 0. So if you have a function of a single variable, any stationary point is wherever the function's first derivative is 0. So this could be either a maximum or a minimum, or it could be some sort of a point of inflection, saddle point. For multivariable functions, this is a point where all the first order partial derivatives are 0. So here, since we can have x, y, lambda, so there are 3 possible variables. Even though lambda is a constant, we don't know what that constant is. We need to find out what lambda is, so that will satisfy the constraint as well as maximize the function, right? So we don't know what that lambda is, so that is a parameter that we have to estimate. So we have 3 first order partial derivatives that we have to calculate, right? And then set that individually equal to 0. So that means the gradient of this function is 0. The key thing is that the solution to the original constraint optimization problem, which is stated here, can always be identified among the stationary points of L, and it is a saddle point of L. And I'm not going to again give proof for this. Proof can be seen in many sources. All right, we are just going to use this idea, this method. Now I'm going to give a simple example to illustrate how this whole idea works. A very simple example: we need to enclose a rectangular field with a fence. Okay, so we have 500 feet of fencing material, and we are going to fence a rectangular field. There is a constraint that the building is, there is an additional information. This is not a constraint. A building is on one side of the field, so we won't need any fencing on that side. So the fencing is going to be needed in 3 sides, and there is a building on the other side, 4th side. So determine the dimensions of the field that will enclose maximum area. So we are looking at what should be the dimension of the field which will enclose maximum area, but we only have 500 feet of fencing material. Okay, so how best can we use all the 500 feet to maximize the area that is obtained inside? So here is how the simple picture can be considered. This side is a building, so we don't need the fence. These are the 3 fences that we build Alright, if we call the vertical distance is y, rectangular, so this also is y, and then the horizontal distance is x. Alright, we have to maximize this area. What is this area? This area is x into y. Okay, building ensures that one side is not fenced. So what is the constraint? What is the function to maximize? Maximize a, which is xy, subject to the constraint that if you take the total length of the perimeter of the fence, that should be 500 feet. That's all you have the fencing material. So you only have one x, you don't have the other x because there is a building. So x plus y, so x plus 2y is 500. We can solve this without Lagrange multiplier. I simply eliminate one of the variables. So eliminate x. X is 500 minus 2y. So the area is y into 500 minus 2y. And we just set dA dy equal to 0, solve for y. Y turns out to be 125 feet. So 2 into 125 is 250. Plus another 250 is 500. So x is 250 feet. Very simple. Why do we need Lagrange multiplier? Of course, in more complex problems, more variables, you will need Lagrange multiplier. But the idea of this, how this problem can be solved, is fairly straightforward. Let us solve this problem with the Lagrange multiplier. Maximize a equals xy, subject to the equality constraint 500 is equal to x plus 2y. So we define the new function, which is xy minus the Lagrange multiplier lambda times the constraint, which is x plus 2y minus 500, and we estimate the gradient. So when you differentiate this function L with respect to x, keeping y constant and lambda constant, you get y minus lambda. When you differentiate with respect to y, keeping x and lambda constant, you get x minus 2 lambda. Then when you differentiate with respect to lambda, keeping x and y constant, you get minus x minus 2y plus 500. All of them are set equal to 0. So from this we can see y is equal to lambda, x equal to 2 lambda, and x equal to 2y. Therefore, substituting these, okay, so I can simply write x here. So minus 2x equal to 500, x equal to 250 feet, y equal to 125 feet. Lambda is also 125. Let us consider another example, a simple example. Maximize f of x comma y is x plus y, subject to the constraint x square plus y square equal to 1. This you can see is a circle of radius 1, and this is a plane. Right? Now again, you can solve this without Lagrange multipliers by substituting for one of the variables, say y. Y is equal to plus or minus square root of 1 minus x square. You can substitute this and then try and maximize the function. But instead of doing that, before using Lagrange multipliers, I am going to use geometry to sort of illustrate what we mean by this maximization. As I said, the function f of x plus y is a plane. The constraint is a circle. So consider the points on the plane that satisfy the constraint. So when we are looking at the maximization subject to the constraint, we are only looking at all those points that satisfy the constraint and looking at amongst those points where is the maximum, right? So here is a picture. So this colored plane is the plane f of x comma y, which is x plus y, and the constraint is the circle x square plus y square equal to 1, right? So if you were to look at x square plus y square equal to 1, this is x, that is y, and this is the circle that is projected onto the plane, basically, right? Or rather, the circle here projected onto the xy plane is this circle. Now these are the points that satisfy x square plus y square equal to 1, and so among these points you can see that the maximum for the function, okay, is at this point, which corresponds to square root of by 2 or 1 by root 2, and the maximum value of the function is square root of 2. The minimum corresponds to this point, which is minus 1 by root 2, x equal to minus 1 by root 2, y is equal to minus 1 by root 2, and the minimum value of the function is minus square root of 2. And this is what is stated here. Now, how do we go about getting this maximum? By Lagrange multipliers. We define the Lagrangian function L as f of x comma y minus lambda into g of x comma y, where lambda is the Lagrange multiplier. So this is basically x plus y minus lambda into 1 minus x square minus y square, and it won't matter whether you wrote this as 1 minus x square minus y square or x square plus y square minus 1, it won't matter. So then we calculate the gradient of the Lagrangian function, and then this basically differentiate with respect to x, keeping y constant. So this will give you 1, and this will give you 2 lambda x plus 2 lambda x. Similarly, you will get 1 plus 2 lambda y, and then when you differentiate with respect to lambda, you will get x squared plus y squared minus 1. All these will be set equal to 0. So this problem, by the way, is from Wikipedia. So from these two equations, you can see this equal to 0 and this equal to 0. See, it gives that x and y are equal, and they both are minus 1 by 2 lambda. And lambda, of course, is not equal to 0. So if you substitute for this, so to solve for what lambda is, use the third equation, right? 1 by 4 lambda square plus 1 by 4 lambda square is equal to 1, which gives lambda is either plus 1 by square root 2 or minus 1 by square root 2. So if you substitute these values, then x and y are either plus square root 2 by 2 or minus square root 2 by 2, which are exactly these 2 points. So for x, y, lambda being 1 by square root 2, 1 by square root 2, and lambda is equal to minus 1 by square root 2, we see that we get the maximum, which is square root of 2. And for the other choice, we get the minimum, which is minus square root of 2. So Lagrange multipliers really are, the method of Lagrange multipliers is a very powerful tool to determine the maximum or minimum, optimum, right, of constrained, equality constrained functions, right? So now come back to the hypothesis of maximum entropy. What is the hypothesis of maximum entropy shown in the two cases that we were looking at? First, let us look at the case of unbiased distribution, where the average score is 3.5. Remember, once again, to sort of refresh your memory, we've been on a bit of a detour. So we are looking at the problem of rolling a 6-sided die. So you can either get a 1, 2, 3, 4, 5 or 6 for each side, and we have thousands of rolls. After thousands of rolls, instead of knowing the micro state of the system, which would be all the thousands of outcomes 1, 2, 1, 4, 5, 3, 6, so on and so forth. Instead of that, we only know an average score. Severely underdetermined system. I only know one number. Right? So, but this average score is 3.5, which corresponds to possibly, hopefully, an unbiased distribution. Let us see if the average score is 3.5, and we say that, from our previous analysis, we said that the rest state, the equilibrium state of a thermodynamic system corresponds to its maximum entropy or maximum multiplicity, and we have the formula for entropy being either Kb ln W or sigma Pi ln Pi. Now let us see what these formulas and this hypothesis of maximum entropy give us in case of a severely underdetermined distribution, which is unbiased, where the average score is 3.5. Now, as we started out saying, the probabilities should add up to 1, and therefore sigma Pi is 1 or sigma dpi, change in Pi, is 0. So we are going to stick to this equality constraint. This is a constraint on the distribution. Now the question that we are asking is, what is this distribution, P1 star, P2 star, P3 star, so on and so forth? What is the set of these values that maximizes this S, entropy, sigma Pi ln Pi, while satisfying this constraint sigma Pi is equal to 1? Sum of all the probabilities should add up to 1, where Pi is the probability of the ith microstate. There are n such microstates because we have rolled n number of times. So now we define the Lagrangian, the function, which is what is being maximized, minus lambda into the equality constraint, which is sigma pi minus 1. Now there are how many variables? N variables, right? So p1, p2, p3, p4, p5, and so on and so forth up to pn. So if I take the gradient of this Lagrangian function, then I will take the partial differential derivative of the Lagrangian function with respect to p1, p2, p3, and so on and so forth up to pn, and set it all equal to 0. Now let us see what is dou s dou p1 for this part. So this gives basically minus 1 minus ln p1. And the other one, if I take the partial derivative of this thing with respect to p1, it gives me simply minus lambda. All the other terms will vanish. Therefore, dou L dou p1 is equal to minus 1 minus ln p1 star. Now because I am setting this equal to 0, right, minus lambda. This gives me ln of p1 star is equal to minus 1 minus lambda. In other words, p1 star is e power minus 1 minus lambda. But notice this, that this ln p1 star is fully a constant, because 1 is a constant and lambda is a constant. We don't know what that constant is yet. We will find out what that constant is by substituting these expressions for all the probabilities into the constraint, like we did in the earlier problems. We will find out, but one thing to notice even before that is that the probability is a constant. So I am calling this any pi star for all the one. It's not just valid for one. I could do this for 1, 2, 3, 4, 5, all these individual states. They would all be the same constant. Okay, so the probabilities of all the individual microstates are the same. One part of the outcome that, okay, what does the hypothesis of maximum entropy give when the distribution is unbiased is, you know, like how we looked at in coin toss, 4 coins tossed, all the 4 coins are equally likely, right? So that was the assumption that we started out with, unbiased distribution, right? So all the microstates have to be equally likely. All the probabilities of all those states should be the same. That is already coming out. And what is that probability? It's a function of lambda. Once we find out what that lambda is, then we will know exactly what that probability is. So at least one part of that analysis that we started out with, 4 coins, 10 coins, 100 coins, and so on and so forth. So if we had such unbiased distribution and we chose this expression for entropy, not necessarily choosing it, this is the expression. I am not giving a proof for why it is so, but if we use this expression and stated the hypothesis of maximize the entropy subject to the constraint that all the sum of all the probabilities should be 1, that is not saying one is equally likely as the other, but just that all the probabilities, if you put all the states, then obviously the probability should be 1 always, right? So that constraint if I put, then for an unbiased distribution I find that every microstate is equally likely. So let us find out what that equally likely probability is for the case of the unbiased distribution. This is the question that we are asking. To get the Lagrange multiplier lambda, we use the constraint sigma pi star is equal to 1. So what we do is divide pi star by this constraint. Okay, so sigma pi star is simply pi star by sigma pi star. This is only 1, right? So I am dividing by 1 essentially, right? And each of this is e power minus 1 minus lambda. So suppose this number is say a. Okay, so what I am looking at, sigma I equal to 1 to n, a plus a, which is a plus a plus a plus a plus a plus a n times. So that is simply n into a. Okay, so that then the exponential terms get cancelled out, and so basically I find that pi star simply is 1 by n without even solving for the Lagrange multiplier lambda. Irrespective of what that Lagrange multiplier lambda is, I find that 1, all the microstates are equally likely, 2, and that particular probability, the equal probability, is simply 1 over the number of all the microstates. This is what we found. If there were total 16 outcomes of tossing 4 coins simultaneously, Each microstate, each sequence had the probability of 1 by 16. So by taking an expression for entropy which captures that multiplicity and saying that the most likely state is the one corresponding to maximum entropy, maximum multiplicity, and see what state results. If I have an unbiased distribution to start with, the probability of all the microstates are equally likely. This is one verification. For an unbiased distributions, all outcomes are equally likely, and the hypothesis of maximum entropy produces that same result. So this is good. In statistical thermodynamics, this unbiased distribution is also described as microcanonical ensemble. What we have discussed so far, this is described in statistical thermodynamics as microcanonical ensemble, though I have not defined ensemble or microcanonical ensemble. All right. The ideas presented here are described as microcanonical ensemble in statistical thermodynamics. Now let us look at again what does the hypothesis of maximum entropy show in the case of a biased distribution. Let us take the average score is 3.6 instead of 3.5. Definitely biased. The higher scores are more likely than the lower scores. Now let us reconsider rolling the die problem with m sides, 6 sides in this case. Right? When a side I appears, say side 1 appears, let the score be epsilon I. After n rolls, the total score is sigma ni times epsilon I. Okay, so the number of times the side I appear. This is one way of adding. Say for example, we were looking at a 6-sided die and we rolled it 10 times. First time you got 1, second time you got 4, third time you got 1, fourth time you got 3, and so on and so forth. Only 2 times suppose you got the score 1. Okay, first time and the third time. Okay, so the number of times score side 1 appeared is 2, and this epsilon I corresponding to that is 1. So 2 times 1 plus how many times did you get 2? How many times did you get 3? So instead of adding each of the outcomes individually, now I am looking at a weighted sum. Right? Note that the sum is not over n rolls. That would be the case if I looked at each roll. Okay, first time I got 1, second time I got 2, third time I got 4, fourth time I got 1, and I added up all of them n times, so that would be sum over all the n. In this weighted sum, I am looking at, there are only 6 possible scores, 1, 2, 3, 4, 5, 6. So the sum is over 6. Okay, where this extra, that's why I am having this extra ni, which says the number of times each side appear. If you rolled a 6-sided die 20 times and suppose you got the following distribution, so side 1 appeared 3 times, side 2 appeared 2 times, 3 appeared 4 times, 4 appeared 4 times, 5 appeared 5 times, 6 appeared 2 times. Let's add this. 5 plus 4 9, 9 plus 4 13, 13 plus 5 18 plus 4 20. 20 times you rolled it. So as I said, when you say the side 1 appears, the number is 1. Side 2 appears, number is 2, and so on and so forth. So then what is this total score? The total score is, instead of saying 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 3 plus 3 plus 3 plus 4 plus 4 plus 4 plus 4 and so on and so forth, I say 1 into 3 plus 2 into 2 plus 3 into 4 plus 4 into 4 plus 5 into 5 plus 6 into 2. The total gives 72. Right? You get this distribution. If you take the probability of finding 1, that is 3 by 20, probability of finding 2 is 1 by 10, probability of finding 3 is 1 by 5, and so on and so forth. Right? The total probability is 1. The average score is basically 72, which is the total that you saw earlier, by 20, that is 3.6. That is why it is biased. Right? So this basically is sigma niei, which is this one, by n. So ni by n is of course pi, the probability, so that is sigma pi ei. So this 3.6 can be obtained by saying 3 by 2 into 1 plus 1 by 10 into 2 plus 1 by 5 into 3 plus 1 by 5 into 4 plus 1 by 4 into 5 plus 1 by 10 into 6. That would give you 3.6. This is a biased distribution, as I mentioned. So now let us ask, what is the likely distribution that maximizes this S in this particular case? What are the constraints? The one constraint is that sigma pi is 1. The second constraint is that the average expected value of the number that you see is 1 or 2 or 3 or 4 or 5 or 6. It's not 3.5, it's not all equally likely. It is basically simply given by this sigma pi ei, and the sum, as you notice, is not over n but it is over m, which is the number of times this thing's number of possible outcomes. Okay, so if we were to consider this hypothesis of maximum entropy, what does the hypothesis of maximum entropy show, right? So since there are two constraints, we consider two Lagrange multipliers. One for this we call alpha, the other for this we call beta. So again we write the function sigma pi log pi minus alpha into this constraint minus beta into this constraint as a Lagrangian function. And now we have the partial derivatives with respect to all pi, and then partial derivative of the Lagrangian function with respect to alpha, and that with respect to beta, set all of them equal to 0. Now if I were to take the dou L dou pi, the first part we already saw, minus 1 minus log pi star, because this function is the same, so the derivative is the same. And for this also we saw it's minus alpha, and here it is quite clear that the derivative is minus beta into epsilon I, so this is equal to 0. Now this means pi star is exponential of minus 1 minus alpha minus beta into epsilon I. One thing to notice right away, that all the microstates are not equally likely, and that is something this maximization of entropy should capture, because you are getting a distribution that is biased, and you already captured that, because not only this expression tells you that not all the states are equally likely, it says that the likelihood or the probability of a microstate depends on the epsilon, right? It depends on the outcome. What is this epsilon I? It's either 1 or 2 or 3 or 4 or 5 or 6. If you roll the 6-sided die 20 times or 200 times or 20,000 times, doesn't matter. The number that you can see is 1 or 2 or 3 or 4 or 5 or 6. Depending on that, you are going to, for each case, you are going to see a different probability. Of course, it also depends on what is the value of alpha and beta, right? So this is an important outcome right away. So we see that pi star is this, e power minus 1 minus alpha into beta minus beta into epsilon I. Now to get the values of the Lagrange multiplier, we use one of the constraints, sigma pi is equal to 1, and then so simply pi star by the sum of all the pi star, right? This is simply dividing by 1, and then I just sum over all of these, all right? And I notice that e power minus 1 minus alpha is a constant, e power minus 1 minus alpha is a constant, so I can take that out and they will get cancelled. So my pi star is simply this. I've eliminated my alpha. I now have e power minus beta ei epsilon I divided by sum of all the e power minus beta epsilon I. To understand what this expression means, let us consider a simpler, even simpler problem. Instead of a 6-sided die, let us just consider a coin, 2-sided coin, right? Then that means m is equal to 2. There are just 2 terms. Let the head for score of head be 1. Let the score of tail be 2. So the average score of an unbiased coin is 1 plus 2 by 2, which is 1.5. Let us take e power minus beta as x. So the probability of finding head or tail is given by probability of finding a head is you have a score of 1 at the top. So this is e power minus beta into 1 by e power minus beta into 1 plus e power minus beta into 2. So e power minus beta is x. So x divided by x plus x square. Similarly, the probability of finding the tail is x square by x plus x square. These are the probabilities. What is the expected score? The expected score is simply epsilon I times pi star, sum over all the possible values of the outcomes. So in this case, so 1 into the probability of head plus 2 into the probability of tail. So I can just sum these two, 1 into this plus 2 into this. So I have x plus 2x square divided by the denominator is the same, x plus x square. So I can simplify this to be 1 plus 2x by 1 plus x. Then I can solve for what is x, which is e power minus beta, in terms of the epsilon, the expected value of the epsilon. So x is simply expected value of epsilon minus 1 divided by 2 minus the expected value of the epsilon. Now let us see what if your average score is 1.5, which is the unbiased case. So if you can get 1 or 2 equally likely, so the average score is 1 plus 2 by 2, which is 1.5. So then if we substitute this to be 1.5, so you get 1.5 minus 1, which is half, divided by 2 minus 1.5, which is also half. So half by half is 1, so x is 1. So then this is 1 by 1 plus 1, this is half. This is 1 by 1 plus 1, this is half. So both probabilities are equal. So again, if this distribution reduces to an unbiased distribution, we get back the exact result that we got earlier, unbiased. For this case, of course, beta will be 0 because x should be 1. Okay. So what if this is biased and your average score is 1.2, which means you are likely to get 1 more than 2, which means you are likely to get head more than tail, right? So you can substitute this 1.2 minus 1 is 0.2, 2 minus 1.2 is 0.8, so that's 0.2 by 0.8, so x is equal to 1 by 4, alright. That means probability of finding a head is 4/5, 80%. Probability of finding a tail is 1/5 or 20%. This is biased to head and beta is greater than 0. Okay, so that is what we are finding out. Now if the expected score is 1.8, then that means 2 is more likely than 1, tail is more likely than head. You can substitute this 1.8 minus 1 is 0.8, 2 minus 1.8 is 0.2. Now it is the other way around, 0.8 by 0.2, so x is equal to 4. You can substitute this and then it's the 4 by 4 plus 16, which is 1/5. 16 by 4 plus 16, 16 by 20, which is 4/5. Now you see that tail is more likely, biased towards tail, and this corresponds to a case of beta less than 0. Why? Because I am getting a value, if beta is less than 0, e power that value will be positive. So I am getting a value of x that is greater than e, which is 4. So what am I seeing here is that each bias distribution corresponds to different values of the Lagrange multiplier. Okay, so when beta is less than 0, I get a certain type of distribution. When beta is greater than 0, I get a certain type of distribution. And when beta is equal to 0, I get an unbiased distribution. Right? So it's as if the second constraint did not even exist. So I get an unbiased distribution. Right? So this means, right? So depending on the value of, depending on the nature of my distribution, I will get different Lagrange multipliers. This is the first conclusion that I come to. Okay. In addition to that, prior conclusions, I can tell you, when I set this Lagrange multiplier to a certain value, in this simple example, beta equal to 0. That's not always true. In this simple example, beta equal to 0. But when I set the Lagrange multiplier to a certain value, then the distribution becomes unbiased. For each type of biased distribution, I will have a separate unique Lagrange multiplier, and I can predict, see, certain types of microstates are more likely, certain types of microstates are less likely. This is important. So I am able to get some information about what kind of states are more likely by maximizing my entropy. The constant, what is this constant Lagrange multiplier? This ensures that my expected value of the score, right, 1 or 2 or 3 or 4, whatever, what is the expected value, the average value, right, that is simply the sum of sigma pi epsilon I, and that is satisfied subject to these probabilities. I should have put a star here. Subject to these probabilities, in other words, subject to the biased distribution, what would be my average value of that epsilon that I am going to see. So if now I take a step back and connect you to the original the example that we talked about, these epsilon i's are the sequences, right, and this is the composition. Now I have a case where not all sequences are equally likely. This is what I wanted to reach towards. Okay, at least present one system, one example where not all outcomes have to be equally likely. What if you had a biased coin? What if you had a biased die? That is what we are trying to look at, right? So in practical systems, it doesn't have to be that all the microstates are equally likely, right? So what if that happens? Subject to those unequal probabilities of the microstate. Okay, so when you add all the corresponding values, suppose your epsilon is say a temperature, all right, or no, suppose this is your average value of internal energy, for example, this is your energy. For each microstate, you have a certain internal energy, all right, you have a certain probability for that internal energy, and then you add up, you get the average value, right? So what is the average value that is going to show up? All right, what is the average value of the internal energy that you're going to measure from a macroscopic perspective? Is this constraint is satisfied by the choice of the constant beta. Suppose, as I said, the expected value of epsilon measures the average or expected value, the energy of the system. In such cases, I am not giving any proof. I'm giving what the value of beta is. Now I've made a leap, right? So I've gone from coin toss and die rolls to a system where I'm looking at molecules and whatnot, right? To thermodynamics, again without any explanation or proof, which you can find in a number of textbooks, some of which I'm listing below, right? There is a book, Dale Bromberg, of course. You can also see Fundamentals of Statistical and Thermal Physics by Frederick Reif. There is a Statistical Thermodynamics by Donald McQuarrie. There are plenty of books. From India, you have Postulation and Statistical Thermodynamics by Y.V.C. Rao. Right? There are plenty of textbooks that are available where this particular expression is derived, but I'm not getting there. I am trying to illustrate the idea of what entropy is. That is our purpose. Our purpose is not to go into statistical thermodynamics, right? But what we are looking at is when we go from microstates, microscopic states to macro states or macroscopic states, when we go through this transition, and we have this property entropy, which is a macroscopic property, which has molecular origins, which is the multiplicity that you measure kb log omega, right, or log w, right, and that particular entropy, you say, to get my rest state or equilibrium state, I consider maximum entropy. And I'm again not giving you the proof for this, but I'm saying that that is equivalent to minimizing your internal energy, right? So when you do this, what is it that you are getting? What you are getting is, if you are looking at measuring the average expected value of the energy, subject to this constraint that not all the states are equally likely, all the microstates are equally likely, then I get a constant of beta to be Kb times T, where Kb is the Boltzmann constant and T is the absolute temperature. This means that for this particular system, temperature is constant. And this constant temperature chooses what kind of your measured expected value of the energy is going to be, subject to maximizing your entropy. So this corresponds to measuring the average available energy of the system corresponding to different fixed values of temperatures. Choose the temperature, you will get a different measured quantity of energy, the available energy, and that will correspond to maximizing the entropy. Choose a different temperature, fixed temperature, you are fixing the temperature, right? You will get a different measured value of the available energy. That will also maximize the entropy. So this is a picture that I am trying to paint of thermodynamic equilibrium. I have just chosen, without any kind of proof, just these 2 bullet points, taken a leap from all these simple examples of coin toss and die throws, right? Saying that when I am fixing my temperature, when I have thermal equilibrium between my system and the surroundings, all right, now that thermal equilibrium is achieved subject to maximizing the entropy of the system and the surroundings, which are in equilibrium with each other, all right? And then corresponding to the choice of the temperature, the available energy in the system will be different, and that will be the average measured value of the energy, and that energy is called the Helmholtz free energy. So what does this mean to say I fix a temperature? To going back to our examples of original examples of the boundaries, fixing the temperature corresponds to having a diathermal wall with an infinite reservoir, so that even if it supplies some energy to the system, or if it takes some energy from the system, its temperature is not going to get changed, and this system is in equilibrium with the infinite reservoir. It is like saying I have a glass of water, and that water is exposed to this atmosphere that has so many air molecules, various molecules which are nitrogen, oxygen, and whatnot, so on and so forth, moisture, H2O, and everything, right? Carbon dioxide and everything, right? So it is that the energy content of that reservoir is so huge. Even if I kept my glass of water that is hot, and if this glass of water loses energy to the environment, the temperature of the environment is not going to be appreciably perturbed at all, and a glass of water will reach from the hot water that it was to the ambient temperature, and that the surface of the water that is exposed to the atmosphere is a diathermal wall. And eventually I fix this particular value of temperature, and now the available energy that I'm measuring is the expected value of the energy, that is Helmholtz free energy. This is a different energy compared to the internal energy of the water itself. The measured energy corresponds to that energy that will maximize my system's entropy. So in statistical thermodynamics, again without any further details, this biased distribution of fixed temperature is described as canonical ensemble. Now similarly, you could posit that I could construct such quote-unquote ensembles corresponding to where pressure is constant, corresponding to where chemical potential is constant, and I will measure different energies. The lectures subsequent to describing this, I will spend one more lecture after this on this maximizing entropy, and using that idea to describe what it means, what temperature means, what pressure means, what chemical potential means. All three have not been defined yet, so we will define that in the next set of lectures. But after that, I will spend one lecture where I obtain what are the different free energies or different measured energies, the expected value of average value of energy of the system when I maintain temperature constant or pressure constant or chemical potential constant and so on and so forth. So basically that will be seen in a separate lecture. Okay. Now with this, I should say that we have come to the end of entropy, but no, there are just a few more ideas. I know this lecture is long, but I hope you can at least listen to this in pieces, in parts, and get a perspective of what entropy is.